So this is what you guys would have done with Teacher Kat in the last episode, in the last lesson, when you learned about exponential equations. So I hope you guys are ready to go to dive into this. Remember, this y equals -3 tells us something very important. We know where this is going to go. We know where this is going to go. Hello, Desmarie. It's lovely to see you as well. It's so lovely to have you with us. Okay. I see someone named Letabo. Letabo, hello. Welcome. I don't know if we've met before, Letabo, but I am the actual grade 10 teacher and not the other two strangers you would have met throughout last week. In that case, welcome to MathsLive. It's lovely to see you. Hello, Vikanyo. Lovely to have you with us. All right, I'm going to give you guys one more minute to try out this question on the screen. It shouldn't take us too long. We should know that we've got our asymptote for our exponential graph, and then we're going to use the information we've been given to find the other value that we need. We need the value of b, okay, because we know what q is. We need to find the value of b. All right. Okay, peeps, I'm not going to waste very much time. Let's have a look at this question very, very quickly, because we do have a lot to talk about today. We're going to be looking at trigonometric graphs today, and that takes up quite a bit of time. So I'm hoping we can get through this in a timely manner. All right, so if we look over here, we know that y is equal to -3. This -3 value is actually my q value, because it's moved my graph, my entire graph down by 3. Right, so this is my q value. So at the moment, I already know that I can go in here and I can say that f of x is equal to b to the power of x plus, not plus cube, -3, right? Because my q value is -3, so I'm going to go -3. Now, in order for me to find the b value, which is what I need, I'm going to change this f of x to y, and I'm going to use the value that they've given us to substitute into the formula that we've got over here. So I know that this is the x value I'm going to put in, and this is the y value I'm going to put in. And then we're going to use those two values to find b. So I'm going to replace x with -2. I'm going to replace y with -7. So -7 is equal to b to the power of -2 minus 3. All right, and then I'm going to take the -3 over to the other side. So I'm going to get -7 plus 3 is equal to b to the -2 can actually be written as 1 over b squared. Anything with a negative exponent needs to be flipped, right? So this is actually 1 over b squared. Now on this side, -7 plus 3 will give us -4. So I'm going to get -4 is equal to 1 over b squared. Right, now to solve for this, I can cross multiply on both sides by b, or find an LCD of b or cross multiply. So I'm going to make this a fraction over 1, cross multiply that way, cross multiply that way. So I'm then going to get -4 b squared is equal to 1, right? And then I'm going to divide by -4. On both sides. So I should get that b squared is equal to -1 over 4, or 1 over -4. What has Teacher Coco done that's weird here? Because technically I'm not going to be able to find the square root of a negative number. Oh, I see what I did. I see what I did. Okay, so maybe let's not make this b to the 1 over b squared. We should keep it as b to the -2, because then that will help us to find the answer that we're looking for here. Okay, so let me see. If I leave this as b to the -2 is equal to -4, I can get b to the -2 is equal to -2 to the power of 2. Negative 2 all squared. There it is. Okay, so this becomes negative 2 squared, like that. Right. Okay, so 1 over b squared is equal to 2 squared over 1. All right. Teacher Cook is not seeing it. What have I forgotten, guys? Something's not right here. Can anybody help me out? Oh no, guys, ma'am's stuck. What are we going to do? Sure, okay. Shall we park this one? I'm going to come back to it. I'm going to solve it while you guys are busy with something else, and then we'll come back to this. All right. Sorry, guys. I'm clearly off my game after being gone for a whole week and a half. I'm sorry about that, but I will figure it out. Okay. Right, I feel like the answer should be 2. So I should have a times b to the power of x. All right, we'll sort it out. Okay, so today we're actually going to be talking about trig functions. I just want to check with everyone. Give me a thumbs up if you've done trig functions at school before, or thumbs down if you have not done trig functions at school. Okay, Desmarie says no. Anybody else? Have you guys managed to do them at school? Okay, Wikanya says yes, Annalisa says no. Okay. All right. Okay, that's okay. I think we're going to try and take it a little bit slow. But okay, let me rather ask this. Rather than saying, have you done trig functions at school? Let me ask, have you started functions? Thumbs up if you have started functions, thumbs down if you have not done functions at all. So if you've done straight line, parabola, hyperbola, exponential, have you guys done that? Okay, Sanalisa says yes. Okay, yes. Okay, because it's a little concerning that you guys haven't done it, or let me not say haven't done it, but that your teachers have not addressed it thus far. Or maybe is it because, just out of curiosity, are you guys on holiday? Am I the only one who's not on holiday yet? Because I'm gonna be honest, I'm gonna be a little mad if everybody's on holiday and I'm the only one still getting up in the morning. Oh, okay. Good, suddenly. So lovely. It's not just me. It's not just me. But I have 2 more weeks of school, not next week. I'm still at school next week. Oh, shame. Oko, I did see. And there were floods in the KZN area as well. Shame. Sorry, man. Are you guys okay though? Is everything okay? I hope everything's fine. Just let us know if you're doing okay. All right. Okay. Let's get stuck into the idea of, that's okay. Okay. As long as everyone's safe, that's okay. All right. So if I said to you guys that I've got a Cartesian plane over here, we know that's 0 degrees, that's 90 degrees. We're going to plot a trig graph on this particular Cartesian plane, right? Because we've done trig graphs before. Like, let's say, for instance, if ma'am tells you that this point over here is the point 4, 3, we know that we can draw a line from the origin to the point, right? And then we can create a triangle by dropping that y value and doing that. And then this will tell us that the x coordinate, or this value over here, if this is my angle theta, this x value from there to there, or the distance there from there to there, is 4. The distance from here to there is the y value, which is 3. And this is r. What can we use to find the r value, guys? What did we say we can use to find the r value? Remember, it's a right-angled triangle. That's it, Desmarie, beautiful. We could use Pythag, of course we could, right? So we know how to do this at a particular point, right? We know how, if they give us a particular point on a Cartesian plane, we can do that. But let's say, for instance, because we want all of our trig functions to they all come from somewhere. When we think of things like special angles, like when we say to you that sine of 30 degrees is equal to 1/2, where do we get the idea that sine of 30 degrees is equal to 1/2? Okay, so what we normally do is we will take our Cartesian plane and we will go from the origin. I really wish that was the origin. Clearly it's not. We're going to go from the origin of our circle, and we're going to draw of our Cartesian plane, and we're going to draw a circle, a perfect circle. And we're going to say that this perfect circle that we've got has a radius of 1. So the distance from there to there is 1 unit, right? Now, I can also tell that the distance from here to there, how many units is it from here to there, guys? How much is that going to be? Does everyone agree that it's going to be? Who's got an idea? If that one is 1 unit, how far or how long is that one also going to be? It is going to be 1 unit. Lovely. This one is going to be 1 unit. So technically what we've got is we've got a circle with 1 unit everywhere around, right? Which is kind of like a simple concept. Ma'am isn't teaching you guys anything new there. We know exactly what that means. Now, the thing that's going to change as we go around our circle is going to be our x values and our y values because of my theta, because of the angle theta. So if I decide to draw my angle theta there, right? If that's my angle theta, my x value is going to be really big and my y value is going to be really tiny, right? But if I decide that I want my theta to be here, okay, if I do that and I make theta that part there, right? We can tell that my x value over here is going to be really small and my y value is going to be really big, right? But what do we know about the purple triangle and the blue triangle? What do we know about the radius of the purple triangle and the blue triangle? I'm going to add in another one. Let's say, for instance, we draw it this way and we go there and we can say this is the negative x side and this is the positive y side. What do I know about this radius and that radius and that radius? What do we know about all of these? All of the r's are what? They're all equal, correct, Sandy? So all of my r values are going to be 1. They're just going to be 1. So what this actually tells us is that our ratios of x and y, it doesn't matter where I draw my x and my y. The Pythag, if I do Pythag to find my radius, whatever my x and y is, the radius that is going to give me will be 1, right? The thing that's going to change is my x and my y values and my theta. My angle is going to either be smaller or my angle is going to be bigger. Sometimes it's even an obtuse angle. There's my theta for that one, right? But my radii for each of these x and y values put together is always going to be 1. All right. But now I can't go around and represent every single one of the triangles that could possibly be formed on this one triangle. It would be the same as me. It would be such a pointless exercise because I would then just have to color in the whole circle with triangles, which doesn't make any sense in order for me to find each of those ratios of x and y. So what we're going to do is instead of looking at this as a circle, we are going to make it 3D. We're going to move these points, this one over here, we're going to move them in that direction. Right. So instead of looking at it face forward like that, we're going to look at it from the side. Can I get a thumbs up? Is everybody understanding what ma'am is saying? Okay. Is everyone okay with this idea? Thumbs up. If you're still confused, I'm happy to explain again. It does get a little bit confusing. Okay, lovely. So instead of us looking at our circle as a full thing like this, I'm going to explain. All right, Buikanyo. So let's say I know that to get from this point, if I get from this point, Buikanyo, and I go all the way around my circle, how many degrees have I gone around? How many degrees have I gone around? Who can give me an answer here? If I go from here and I go full revolution, that's going to give me 360 degrees, correct. But now the problem is, Buikanyo, that if I had to draw a triangle, I would have to draw a triangle at 1 degree, and at 2 degrees, and at 3 degrees, and at 4 degrees, 5 degrees, 6, 7, 8. Do you see how, if I wanted to draw every single triangle, they would all be squished up together in a space where we wouldn't be able to see what's happening? Am I making sense? So instead of us drawing all of that in a circle, what we can do is we can turn our 360 degrees into a flat line. Therefore, we can see what's happening to each of our x's and our y's and our r value at every point from 0 up until 360 degrees. Okay, that then brings in, because we normally use sine, cos, and tan here, we would be looking at something like this. So instead of drawing it all in a circle, what we've done is we've taken our circle and we've unraveled it. So we've started at 0 here, and we've written it on a straight line so we can see what each of our values is doing one at a time. Okay, does that make sense, Buikanyo? Okay, so now over here, I can see exactly what's happening at 1 degree. I can see, or let's call that 5 degrees. I can see what's happening at 5 degrees in this direction. I can see what's happening at 45 degrees in this direction. And I can see what's happening at 90 degrees in this direction. And everything in between, I'm going to be able to say, okay, so the value that they make, that would be my x value and my y value over there, according to my angle theta. Okay, or in this case, we're going to look at the y value and the r value. Okay, there. I want us to note also, because we're comparing everything at the same point, do we see how the sine graph has an amplitude, or the highest point is 1. And if we look over here, what is the lowest point that we've got? -1. Because on my circle, as we look at my circle, we've made every single radius going around 1, which means the point over here will be 0 and -1. That would be the lowest point. The point over here would be 1 and 0. This point would be -1 and 0. So my graph of sine and cos and tan on the graph will only go from 1, will go up 1 and come down to -1. It won't go any further. I want everybody to do me a favor. I want you to go into your calculator and click Shift Cos of 2,3. Tell me what your calculator says. Shift cos of 2.3. It gives an error. It does, right? Because when we are comparing every single ratio, our ratio is always an answer less than 1. Okay, and if you look at our cos graph, our values for theta will only give us a value between 1 and -1. Thumbs up. Is everybody understanding what ma'am is saying? We have chosen each of our ratios to start at 1. They all have a radius of 1, so they will only go from 1 to -1 because of this. So you cannot have shift cos of 3 or 5 or 7, because the number that you need in here needs to be a 0, something. So in here, you will only be able to get numbers between 0 and 1 as an answer. Okay, so your cos 350 will always give you a number smaller than 1. Your cos 282 will always give you a number smaller than 1. You can test that. For your sine as well, it will also only give us those values. All right. The only different one is going to be cos. All right, now we're going to introduce the mother graphs. And with this, we're going to introduce some new terminology. So we need to understand a couple of things. So these three graphs that we're looking at over here are graphs of sine x, cos x, and tan x. Now, the way we draw these is we look at the most significant points on our Cartesian plane. So we want to go and look for sine of 0, because 0 is a signpost, right? 0 is a signpost. So 0 over there, sine of 90, sine of 180, sine of 270, and sine of 360. Now, everybody, I hope everybody's got their calculator at the ready. I want us to go ahead and we're going to replace x with the following values. Let's start with sine. We're going to look for sine of 0. Tell me, everyone, what is sine of 0 degrees? If you punch this into your calculator, you don't need to click shift. We're not looking for an angle. We're just looking for the answer. What is sine of 0? Find me sine of 90 degrees. Find me sine of 180. Thank you, Kat. Lovely. Sine of 270 and sine of 360. We're going to use these these 5 signposts. Good. So we know that sine of 0 is 0. And you can see that at 0 degrees, our graph starts there. Thank you, Desmarie, for the next one. Good. Sine of 0 degrees is at 0. Sine of 90 degrees is at 1. So we know that our graph will go through the point 1. What is sine of 180 degrees? 0. Good. Sine of 180 degrees is 0. It's not negative 1, just 1. 1. Sine of 180 is 0. What is sine of 270? Sine of 270 would give us negative 1. Good. Sine of 270 is negative 1. And then sine of 360 is 0. Correct. All right. So what we've done universally, mathematically, is we've chosen the radius of any right-angled triangle we would use trigonometry with to have a radius of 1. And if we do this, we end up with a sine graph that looks like this. That means if we had put in sine of 30 degrees, it would give us a half. So that would be somewhere there. Sine of 45 degrees would give us 1/√2. Sine of 60 degrees would give us something else. And all of these points put together would give us that. If we looked at all the points here, sine 110, sine 150, all of them put together would give us a graph that looks like this. When we look at it on the Cartesian plane, we would just have a triangle, a triangle, a triangle, a triangle, a triangle. It was going to get way too messy for us to see anything. So instead of looking at it this way, we can turn it flat and look at it this way. Thumbs up. Is everybody okay with what ma'am has described here? We all good? Right. Oh, cool stuff. All right. Now, that does not mean that this graph will not change. Okay. Again, this is just the mother graph. The mother graph of sine looks like this. So if we're looking for the graph of sine x, it will have these 5 signposts. Okay, let's look at the mother graph of cos x. And for that, we're going to do the exact same thing we did for sine. Instead, we're going to use cos instead. So we're going to look for cos of 0, cos of 90, cos of 180, cos of 270, and cos of 360. All right, let's find those values. Cos of 0?
1.
Beautiful. Thank you, Bitanyo. Good. Cos of 90 degrees?
0.
0. Beautiful. Cos of 180?
-1.
-1. Cos of 270?
0.
Beautiful. And cos of 360?
1.
Beautifully said, my darling. Well done. Okay, I'm sure Bukanya was reading it off the screen, but that's good. That's what we want. Right, that's exactly what we want. Okay, so there we go. If we look at the mother graph for cos, the cos mother graph should look like this. It should start at 1. All the values should get smaller and smaller and smaller until they get 0 down the negative side. And then at -1, it starts coming back up again, back to 0 and 1. Are we noticing, grade 10s, how this graph starts at 0, goes up to 1, goes past 0, goes to -1, and back at 0. The cos graph starts at 1, goes to 0, -1, 0, and ends up back at 1. But it never goes beyond 1 or beyond -1. They are only within the scope of the radius that we've set for our triangles. Okay, because each triangle that we've set has a scope of cos x, or of 1 and -1, the radius on either side. Okay, so the tan mother graph is a little bit different to the other two, I'll admit. Okay, in that tan repeats itself every 180 degrees. Okay, so it repeats itself every 180 degrees. We're not going to go all the way to 360. We're going to stop at 180. But because this is half the graph, in order for us to signpost for this, we will not be looking at 0, 90, 180. We're going to half all of those things so we can see everything that's happening in between. So we're going to look for tan of 0 degrees. Then we're going to look for tan of 45 degrees. We're going to look for tan of 90 degrees. We're going to look at tan of 135 degrees. And then we're going to look at tan of 180 degrees. All right. And somewhere we're going to run into a problem. I want somebody to tell me when they get to the problem. Let's start with tan of 0. Who's got an answer for me for tan of 0?
It's 0.
Beautiful. It's 0. Good. What's tan of 45? Tan of 45 degrees would give us how much? Anybody got an answer for me? Tan of 45? Sorry, that T was bothering me. Tan of 45 is?
It's 1.
1. Good. Tan of 45 is 1. What about tan of 90 degrees?
It says error.
Just say error. And it's supposed to say error. It's actually undefined, and we'll talk about why. Right, it's undefined. What about tan of 135?
-1.
-1, good. And tan of 180?
0.
Excellent, 0. Okay, good. So we can see where these points are. There's tan of 0 is over there, 0. Tan of 45 would be over here, in the middle over here, right next to 1. So 45 degrees would be here. Right, now at tan of 90 degrees, we're going to have an issue. There's a, what do we call this dotted line? Who remembers? It shows up in the hyperbola and in the exponential graph again. Who remembers what this dotted line that my graph can't cross is called? Do you remember what this line is called? Remember, in a hyperbola, you draw your hyperbola like this, and then there'd be a dotted line like this where my graph cannot cross. What do we call that line again? Who can remember? Bonus points for who can remember. Because technically we should already know. Many of you guys have already written maths. It starts with an A. I'll give you guys a hint. It starts with an A, A-S-Y. Anybody?
Isotopes.
That's the one. Good. It's the asymptote, right? Now, remember where the asymptote actually comes from. grade 10s. If I say to you guys that I've got 2 over x, what value can x not equal? What value can x not be equal to? What number is going to be problematic there? X cannot equal what? Okay, what would make this undefined? Who can remember? So, just want to check. Yes, correct, Kat. Absolutely. Right, yes. It is 0. X cannot equal 0 because anything divided by 0 is going to give us an undefined function. Yes? So in order for tan of 90 to give us a problem, let's go ahead and look at our Cartesian plane very quickly. Right? At tan of 90, I know that tan on the Cartesian plane is equal to my y value over my x value. That's tan of theta, right? That's tan of theta is equal to y over x, or opposite over adjacent, right? But this particular graph over here, at the point 90, this circle at the point 90 has the coordinates 0 and 1, because it's a y-intercept. So my coordinates there are 0 and 1. Now, if I had to put this into the calculator, right, or if I had to put these two values in, I'm going to get that tan at 90 degrees is equal to my y value, which is 1, over my x value, which is 0. And that's going to give me an undefined value. And that is why my tan of 90 degrees gives us a maths error. We're not going to be able to find a value. Thumbs up. Does everybody understand what ma'am has said? Are we all good? Are we all understanding where the asymptote comes from? Lovely, Buikanyo. Desiree says, for now, I'm not going to be mean today, I promise. Everything's just going to be fine. Okay, all right. So if we look at that, if we look at our graph over here, we know that tan is equal to y over x. Which other point on my tan graph is going to be problematic? I know that tan of 90 degrees is problematic. Which other point on my tan graph is going to be problematic? What degrees? Something degrees will also give us a maths error. Where are we seeing it?
270 degrees.
100% at 270 degrees. Because down here, I'm going to get that tan of 270 degrees is equal to my y value, which is -1, over my x value, which is 0. Again, I'm going to get an undefined value. So that's why we have this asymptote at 90 degrees and that asymptote at 270 degrees. All right, so everything that ma'am has said here is very, very important. It's going to be coupled with the following things: the period, the amplitude, the vertical shift, and the asymptote. Now, the asymptote really only exists for tan, because tan is the only one that has an asymptote. But we're going to talk about how, where these things actually come from and what they mean. Okay, so some of these words should look familiar to you. Words like period and amplitude, if you do physics, you should have seen these already somewhere before. Okay, which is actually quite apt, because by the time you get to first year university, maths and physics are pretty much the same thing. You can't take maths without physics, and you can't take physics without maths. Okay, it just happens to be that way. You have to take both. Okay. Unfortunately, you can't escape, suddenly, so there's no escaping. All right, so we're going to look for each of these for the mother graphs of sine, cos, and tan. Now, our period is how long it takes the graph to make a full revolution. It takes my graph to make one full wave, to make a full wave. Okay, so if we look at our sine graph, let's look at our sine graph. What is the period of my of my sine graph? How long does it take my sine mother graph to make
0 and
one?
360.
Correct. Okay. So we're not going to say that. We're just going to say that the period is 360. Okay. It goes from 0 to 360, but you're not wrong, my darling. We're just going to say that it takes 360 because it starts at 0 and it goes to 360. Okay. Let's talk about the period of my cos graph. What is the period of my cos mother graph? How long does it take my mother graph to make a full shape?
1 and -3. I mean 1 and -1.
Remember, we wanted to make a full wave. What's the degrees it would take for it to make a full wave? It goes from 0 degrees all the way up until
360.
360. Yes, correct, my darling. Good. 360. Yes, it takes 360. Now, the tan one is going to be different. What is the period of my tan graph? How long does it take for my graph to start repeating itself? I'm going to do this. I'm going to draw a straight line down there because we went from 0 to 180. So the period of my tan graph is actually how much? Instead of 360, my tan graph will repeat itself after how many degrees? I've given you a hint, guys. I've literally drawn the blue line exactly where it is. Okay. The period of my tan graph is going to be, yes, correct, Sally. Good, 180 degrees. Okay. So basically what happens is my tan graph draws this part, much like a hyperbola would. It would draw that part, it would skip the asymptote and then draw that part up until 0. And then it would start again. It would draw the upper part, skip the asymptote, draw the bottom part. So my period is 180. Okay, so these are things we need to know, grade 10s. Please make sure that you're writing them down. It's very, very important. Okay, the amplitude. The amplitude is how far up from the origin my graph goes. From the origin, and we'll speak about why ma'am says the origin specifically. Okay, so if we look at this, we can tell that every single one of these graphs start at the point 0. They go up a certain amount from the origin. So if we look at our sine graph, it goes from 0 up to 1. So the amplitude
1 and -1.
And that's what I was hoping we wouldn't say. The amplitude is just 1. Okay, the amplitude is just 1. I know that my graph grows from 1 all the way to -1, right? It does. It goes from 1 to -1. But that's why ma'am says that the amplitude is how far up my graph goes from the origin, just from the origin. So we're just looking at the distance from the origin up to its highest point. How many units is that? From the origin to there, my amplitude is just 1. Okay, now the origin is always going to be the part that kind of cuts my graph into 2, like that. All right, so if we look at the graph of cos, what is the amplitude of my cos graph going to be? If I look at it from the origin, going up, even going down, how many units down does it go? That's it. Correct, Sally. It goes up or down, just 1, right? Now, let's look at our tan graph. What is the amplitude of my tan graph? Where does my tan graph turn and come back? Does it turn and come back? Does it turn and come back? Nope, it doesn't. It doesn't. So my tan graph, does my tan graph have an amplitude? No. No amplitude. Okay, because it cannot go past the asymptote. It's just going to keep going up, 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 and get as close as possible to the asymptote, but it will never touch. So both the asymptote and my tan graph will continue to go up, 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 up. They will never actually ever touch each other. So my tan graph does not have an amplitude because there isn't a point from the origin where it touches and then starts coming back down. Okay. All right. Let's look at the vertical shift. Now, because we are looking at graphs, there is a chance that we might take our graph and move it. We might pick the whole graph up and put it there and move it up like that. We could do that, right? Or we could take our cos graph and instead of drawing it like this, we could draw it like that. Right? Like that. We could flip it over or we could move it down. We could move it there and do that. Okay. So all the things that we could do to like a hyperbola or a parabola, we can also do these to cos graphs. So the vertical shift of my graph, just like when we're doing normal functions, when we're doing a parabola, hyperbola, all of those, my vertical shift is the Q. It'll be the Q value that we're looking at. All right. That would be my vertical shift. In this case, in the case of my sine graph, because my sine graph is drawn exactly where it needs to be drawn, the vertical shift for my mother graph, or the Q for my mother graph, is just equal to 0. We haven't moved it up or down. Same with cos. Q is equal to 0. We haven't moved it. And same with our tan graph. Q will equal 0. Then we've talked about the asymptote. We know that the only graph that has an asymptote from our trig graphs is our tan graph. Only tan has an asymptote at 90 degrees and at 270 degrees. Okay. All right. I'm going to ask for a thumbs up. Is everybody still okay? It's a lot of information to take in. I'll be very honest. There is quite a lot for us to remember and learn. How are we feeling about all the information we've received? Are we all good? Okay. Because I want to add in one more thing before I continue with the rest of it, because I want us to be very sure that we're understanding exactly what's happening here. Okay. I've got one thumbs up. I hope everybody else is also with me still. Okay. All right. Cool. Okay, so here's one thing that we need to learn about the idea of a revolution. Okay. The idea of a revolution. I'm going to ask a very obvious question. I hope you guys just indulge me for a little bit, right? If I go from 0 all the way around my circle, where do I land? If I go all the way around, at what degrees do I land?
360 degrees.
Beautiful. I land at 360 degrees. Ah, Wikanyo, you're just doing the most today. I love it. Okay. Now, let me ask you guys, where would I land if I went to 720 degrees? What would that tell me? Think about it carefully. I know a full revolution is 360 degrees. If I had to go 720 degrees, where would that put me? Where would that put me?
180, I think.
No, not quite. Saneliso says 2.5. I don't know about 2.5, Saneliso. Okay, let me see if everybody's in agreement with me. Right, if I land at 3, if I need to go to 720 degrees, if I start at 0, I'm going to go all the way around, and then I'm going to land at 360 again. And then if I add 10 degrees, I'm going to be at 370. And then I add 20 degrees, that's 380. And I go around 390, 400, 410, 410, 450, come around, come around, come around. land at a spot, keep going, keep going, keep going. Where would I land if I was going to 720? Where would I land? That's it, Sally. Beautiful. I would literally go all the way around and land back again at 360. Is everybody understanding what ma'am's saying? Give me a thumbs up. Are you guys with me there? Everybody got the idea there? Good. Lovely. Okay. So if I go all the way around to 270 or to 720, I'm going to end up at 360 again. So when we're looking at the sine graph, if my sine graph has been drawn from 0 to 360, or let me draw it a little bit smaller to make my point. Right. If my graph has been drawn from 0, goes up all the way to 1, back down to 180, at 0, down to -1, and then again at 360, this is 180. That point there is 90 degrees. This over here is 270. That point right there is at -1. And that point is at 1. Right. Now, if I had to go to 270, this is 360. This point over here is 360. If I had to go to 720, what kind of shape am I drawing in here? From 360 to 720, what kind of shape are we going to draw? I know that from 0 to 360 goes up, comes down, back to 360. What would it look if I went from 360 to 361 and I started going in the other direction, or I kept going? What would my graph look like? What are we thinking? Would my graph, oh, let me ask this question. Would the graph change? Would the shape of my graph from 360 to 720, would the graphs change anyway? No, it wouldn't. It would be the exact same graph because I went around this exact same circle just 2 times. I went around the same circle twice. Just from there, ooh, and that's definitely a terrible drawing. Sorry, guys. I went from there to there and back down and again at 720, right? That point over there will just be 1, and that point over there again will be -1. All right. What would happen then, guys, if I went to 1080? Or 1180, is it? No, it's 1080. What would happen then? If I went, because from 0 to 360 and then from 360 to 720, would the shape change? No, it's going to be the exact same shape. Again, going all the way through. The shape is not going to change. Here's my next question, grade 10s. How many times can I draw this? How many times can I go around and around and around and around on my circle? And how many times can I draw the same sine wave? The answer should be obvious at this point. I can just add another 360 and draw another one, add another 360 and draw another one, add another 360 and draw another one. How many of these graphs can I draw? Anybody got an idea? An infinite number, correct. Right, but don't forget, guys, infinity doesn't only go positive infinity. It doesn't only go positive infinity. That means I can take this graph and I can also draw it in this direction. That's just going to be -360. And then another one gets me to -720. And then another one will get me to -1080, like that, like that, like that. But I want us to look at something very, very carefully. Let's choose the point 1/2. We're going to go ahead and choose the point 1/2. Okay. If I go to my tan graph and I go to the point 1/2 there, okay, there. and then I draw a straight line across like that. Okay, my graph is going to cut the same spot more than once. Okay. And if my graph kept going, I would cut again there. And then it would come back down and I would cut again there. Right. Now, this point over here at the 1.5, that point over there is at 30 degrees. And that point over there is at 150 degrees. I want you guys to do me a favor. Go into your calculator, type in sine of 30 for me, and tell me what answer you get. Sine of 30 gives us how much?
A half.
It gives us half. Good. I also want you to put in sine of 150 for me.
Give us a half.
It also gives us a half. Good. So because this thing is a circle that keeps coming back around and back around, if I go from 30 and I add 360, I'm going to end up at that spot again. Now I know that that was 30, so this spot over here needs to be 390. So I want you guys to go into your calculator, punch in sine of 390, and tell me what your calculator says.
A half.
There's a half again, right? So if I go to 150 and I add 360 to 150, that's going to put me at what? 360 plus 150 would give us 510. Punch in sine of 510. Unless I got it wrong. I hope I didn't.
It's a half.
It's also a half, right? Because on the circle, if I had to look for sine of 30 degrees, if this was sine of 30 degrees, my x value would be, I don't know. Okay, we can choose a value. My y value would be 1, and my r value would be 2, and I would get sine of 30 is a half. But now if I pull a full revolution again, all the way around, I'm going to end up at the exact same point again. And then if I add another 360, I'm going to end up at the exact same point again. So if I had to draw my sine and my cos and my tan graph, and I keep drawing and keep drawing and keep drawing and keep drawing, I'm going to end up at the same answer every time I add 360. Give me a thumbs up, grade 10s, if what ma'am has just said makes sense. We can test this with cos of 60 as well, right? If you punch in cos of 60 degrees, it's going to give us half. It's a half, right? So go ahead and add 360 to cos of 60. That's going to give you 420. Go punch cos of 420 into your calculator and tell me how much it gives you.
A half.
It gives us a half again. 420 would give us a half again. Over here also at cos of 300. At cos of 300, we're also going to get a half. But if we take 300 plus 360, it's also going to give us a half again. Are we seeing how all of these things come together, guys? It's very important that we understand that when we are looking at this graph, when we are looking at the mother graph of sine, they've only given us half a graph. But it doesn't mean that there aren't other numbers that would give us the exact same point. Because on a circle, I can keep going revolution, revolution, again and again and again. And I'm going to end up at the exact same point every single time that I add 360. Okay, and I'm going to stop the lesson here because if I go any further, we're going to get a little bit lost. Okay, but before we do go, I'm going to ask on a scale of 1 to 10, 1 being, ma'am, you spoke Greek, you spoke Japanese the whole lesson and I didn't hear anything. 10 being, I'm with you, ma'am, I got you, I think I know what you're saying. Where are we sitting? 1 being no, 10 being yes, got this. Lovely. I'm loving that Sally's at a 10 out of 10. I'm seeing Oko's at 6, Tiamo at 6, Desmarie at 7. That's okay, guys, because we're still going to put all of this stuff into practice in the next lesson, and then you'll be able to understand as we go. Okay, but the one thing, that's okay, Oko. Well done, Bikanyo. All right, the one thing that I want us to bear in mind, the one thing that I want us to always remember is that these graphs, the graph of sine x, the graph of cos x, and the graph of tan x are called the mother graphs. I call them the mother graphs. So I need you guys to remember that if ma'am ever references the mother graph, she's talking about the simple graphs that we've drawn using 0 and 90 degrees and 180 degrees and 270 and 360. Because when we come into the next lesson, I'm going to say to you guys, okay, guys, something on the mother graph has changed. And then you need to figure out, no, man, my mother graph normally looks like this. How did it move from this to that? Then you can be like, oh, they picked up the graph and they moved it up, or they picked up the graph and they moved it down, or they squished it together, or they stretched it apart. It will always be something like that. But we're going to look at what happens when we do that. We're going to take these mother graphs and we're going to stretch them this way, and we're going to stretch them in that direction, and then we're going to pick up the whole graph after stretching it, and we're going to move it up, and we're going to move it down. Okay, so I want you guys to bear in mind everything that ma'am has said today. It is the foundation of what we're going to be doing on Wednesday. All right. Okay, somebody just brought something up that's very,